Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into wherever you are. There's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the universe feels very far away, or perhaps closer than you think? Tonight we're going to explore something that might surprise you about the place we call home. Our galaxy, the Milky Way, that vast collection of stars that seems impossibly large when we look up at the night sky, is actually rather small. In fact, compared to some of the cosmic giants out there, it's embarrassingly tiny. We'll discover what this really means, understand why galaxies come in such different sizes, contemplate whether size actually matters in the grand scheme of things, and find a kind of peace in our modest cosmic address. It's a journey that spans billions of light years and touches on the very nature of existence itself. But don't worry, this isn't going to be a lecture filled with overwhelming numbers and incomprehensible distances. Instead, we'll move slowly and carefully through the universe, taking our time with each discovery, each comparison, each moment of wonder. By the end, I think you'll find that being small in a vast universe isn't diminishing at all. In fact, there's something rather beautiful about it. If you enjoy these calm explorations of space and our place within it, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, night after night, as we drift through the cosmos together. So settle in, let your shoulders drop, take a slow breath, and feel your chest rise and fall. Let's begin our slow drift through the vastness of space, starting with the realization that our home galaxy, as magnificent as it is just a modest island in an ocean of giants. There's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold. The universe isn't going anywhere, and neither are we. Let's start with what we know about our home. The Milky Way is a barred spiral galaxy, which means it has a distinctive shape with arms that spiral outward from a central bar of stars. Picture a pinwheel made of light, slowly rotating through the darkness of space. It's the galaxy that contains our sun, our solar system, and everything we've ever known. The numbers, when you first encounter them, seem impossibly large. The Milky Way contains somewhere between 200 billion and 400 billion stars. That's a range so vast that the uncertainty alone represents hundreds of billions of suns. Each one of those stars is a world unto itself, many with their own planets, their own stories, their own potential for harbouring life. The galaxy stretches roughly 100,000 light-years from edge to edge, a distance so enormous that light itself, travelling at 186,000 miles per second, takes 100,000 years to cross it. At the centre of our galaxy sits something remarkable and terrifying, a supermassive black hole called Sagittarius A star, pronounced __0__. This cosmic monster weighs approximately 4 million times more than our Sun, and yet it occupies a space relatively compact for such immense mass. It's the gravitational anchor around which our entire galaxy slowly wheels, completing one rotation roughly every 200 million years. Our solar system, located about 26,000 light-years from the galactic centre, is moving through space at a speed of about 500,000 miles per hour, and yet from our perspective, everything seems perfectly still. The Milky Way has a thickness too, not uniform across its span, but averaging about 1,000 light-years in the disk where most stars reside, and puffing out to about 10,000 light-years in the central bulge. Imagine a dinner plate with a slight mound in the middle, and you have the basic shape. The spiral arms, named for the constellations they appear near when viewed from Earth, the Perseus arm, the Norma arm, the Scutum Centaurus arm, and others, contain most of the galaxy's active star formation regions. Places where new suns are being born even now. These are the statistics of our home, 2 to 400 billion stars, 100,000 light-years across, 4 million solar masses at the centre, 500,000 miles per hour through space. These numbers defined the limits of our cosmic understanding for a very long time. When we first began to grasp the true scale of the Milky Way in the early 20th century, it seemed to encompass everything. The entire universe contained within this one magnificent structure. And then we discovered we were wrong. And that discovery, that humbling realization, is where our story truly begins. Because what we thought was everything turned out to be just one galaxy among billions, and not even a particularly impressive one. The revelation came gradually, as most profound truths do. In the 1920s and 30s, as astronomers like Edwin Hubble turned increasingly powerful telescopes toward fuzzy patches of light in the sky, they discovered something extraordinary. Those patches weren't nebulae within our own galaxy, as many had assumed. They were separate galaxies entirely, each one a collection of billions or trillions of stars, scattered throughout the universe at incomprehensible distances. With this discovery came a new ability: comparison. And when we began comparing the Milky Way to its cosmic neighbours, we encountered an uncomfortable reality. Our galaxy, which had seemed so impressively vast, was actually rather modest. Not the smallest, certainly, but nowhere near the largest. It was like discovering that what you thought was a mansion was actually just a comfortable cottage in a neighbourhood of castles and cathedrals. Consider Andromeda, our nearest large galactic neighbour, located approximately 2.5 million light-years away. Andromeda is a spiral galaxy like the Milky Way, with a similar structure and shape, but it's substantially larger. Where the Milky Way stretches 100,000 light-years across, Andromeda extends roughly 220,000 light-years. It contains approximately 1 trillion stars, more than twice the number in our galaxy. Possibly 3 times as many. Its central supermassive black hole weighs in at somewhere between 110 million and 230 million solar masses, dwarfing our comparatively modest 4 million solar mass Sagittarius A star. But Andromeda, large as it is, isn't even close to the giants of the galactic world. There are elliptical galaxies out there, vast collections of stars that have lost their spiral structure and formed into enormous spheroids that make both the Milky Way and Andromeda look positively tiny. IC1101, located in the Abell 2029 galaxy cluster about 1 billion light-years away, stretches 6 million light-years across. 6 million. That's 60 times the diameter of the Milky Way. It contains an estimated 100 trillion stars, enough to distribute 1,000 stars to every human who has ever lived and still have plenty left over. These numbers can become numbing in their enormity, so let's think about them differently. If you were to create a scale model where the Milky Way was the size of the United States, Andromeda would be the size of North America and Greenland combined. IC1101 would be larger than the entire planet Earth. The comparison isn't even close. We're not just smaller, we're dramatically, embarrassingly smaller than the galactic giants that populate the universe. And this raises a question that we'll be exploring throughout the night. Does size matter? Is a galaxy's value, its significance, somehow tied to how many stars it contains or how far it stretches? Or is there something else, something more subtle and more meaningful, that determines what makes a galaxy important? Hold that thought as we continue, because the answer is more complicated and more beautiful than you might expect. To understand how we came to know that the Milky Way is small, we need to appreciate how difficult it was to measure anything in space at all. For most of human history, the stars were simply lights in the sky, fixed to a celestial sphere that rotated around the Earth. Distance was a meaningless concept when you believed everything was equally far away, just decorations on the dome of heaven. The first breakthrough came in the early 1800s, when astronomers began to detect parallax, the apparent shift in a star's position as Earth moves around the Sun. Friedrich Bessel measured the parallax of the star 61 Cygni in 1838, determining it was about 11 light-years away. This was revolutionary. Suddenly, the universe had depth. The stars weren't affixed to a sphere. They were scattered through space at varying distances, some close, some unimaginably far. But even with parallax, astronomers could only measure distances to relatively nearby stars. Beyond a few thousand light years, parallax became too small to detect with the instruments of the time. The true scale of the Milky Way remained mysterious. Some astronomers thought it might be only a few thousand light years across. Others argued for much larger dimensions. There was no way to know for certain. The breakthrough came through the work of a woman whose name deserves to be more widely known, Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 1900s. Leavitt studied a type of variable star called Cepheid variables. These stars pulse with regular periods, brightening and dimming in predictable patterns. What Leavitt discovered, through painstaking observation of thousands of stars, was that the period of a Cepheid's pulsation was directly related to its intrinsic brightness. A Cepheid that pulsed slowly was intrinsically brighter than one that pulsed quickly. This discovery was revolutionary because it provided a standard candle for measuring cosmic distances. If you could identify a Cepheid variable in a distant cluster or nebula, measure its period, and calculate its intrinsic brightness, you could then determine how far away it must be based on how bright it appeared. It was like finding a light bulb of known wattage in the distance and using its apparent dimness to calculate how far away it was. Edwin Hubble used Leavitt's work in the 1920s to measure the distance to Andromeda, then called the Andromeda Nebula. He found Cepheid variables in Andromeda and used them to determine that this _quote_2_ was in fact far outside the Milky Way, a separate galaxy entirely. The implications were staggering. Not only was the universe much larger than anyone had imagined, but the Milky Way was just one galaxy among countless others. From there, astronomers developed increasingly sophisticated methods for measuring cosmic distances. Redshift measurements, which detect how much light from distant galaxies has been stretched by the expansion of the universe. Type 1. A supernova, exploding stars that serve as even more powerful standard candles. Each new technique extended our reach further into the cosmos, and with each extension came the discovery of more galaxies, larger galaxies that put our own modest Milky Way into humbling perspective. We went from believing we were the centre of everything to realising we were one small part of something incomprehensibly vast, and that realisation is one of the most important in human history. It changed how we see ourselves, how we understand our place, how we think about our significance. And it all started with the simple question, how far away are the stars? The answer, it turned out, was much farther than we ever imagined. Before we can truly understand why the Milky Way is small, we need to understand what a galaxy actually is, what holds it together, and how it works. Let's take our time with this, because the structure of a galaxy is one of the most beautiful examples of cosmic architecture in the universe. A spiral galaxy like the Milky Way consists of several distinct components, each playing its own role in the galactic ecosystem. At the very centre sits the galactic bulge, a densely packed sphere of older stars, typically yellower and redder than the stars in the disk. These are ancient suns, many of them formed when the galaxy was young, now orbiting peacefully in the gravitational well of the central supermassive black hole. The bulge is hot and crowded, with stars packed much more tightly than in the neighbourhoods we're familiar with. Extending outward from the bulge is the galactic disk, a flattened structure where most of the galaxy's stars, gas and dust reside. The disk is where we find the spiral arms, those beautiful curved structures that give spiral galaxies their distinctive appearance. But here's something fascinating. The spiral arms aren't fixed structures. They're not like the arms of a starfish, permanently attached and rotating as one piece. Instead, they're density waves, regions where stars and gas temporarily crowd together as they orbit the galactic centre at different speeds. Think of it like a traffic jam on a highway. Cars enter the jam from behind, slow down, then exit at the front, but the traffic jam itself stays more or less in the same place. Similarly, stars drift into a spiral arm, spend some time there, then drift out the other side, but the arm itself persists. This explains why spiral arms are such prominent sites of star formation. The density wave compresses gas clouds, triggering them to collapse and form new stars. The arms are literally stellar nurseries, birthing grounds for new suns. Surrounding the disk is the galactic halo, a roughly spherical region that extends well beyond the visible edge of the galaxy. The halo contains globular clusters, ancient balls of stars that orbit the galaxy on long elliptical paths, and something even more mysterious: dark matter. We can't see dark matter directly. It neither emits nor absorbs light, but we know it's there because of its gravitational effects. The halo contains far more dark matter than visible matter, perhaps 10 times as much, and it's this invisible substance that provides most of the gravitational glue holding the galaxy together. The total mass of the Milky Way, including all its dark matter, is estimated to be somewhere between 1 trillion and 1.5 trillion solar masses. That sounds impressive until you remember that most of that mass is invisible, and even with it, we're still on the smaller end of galactic sizes. The dark matter extends the Milky Way's gravitational influence out to distances of perhaps 600,000 light-years or more, far beyond the visible edge of the galaxy, creating an invisible architecture that shapes the orbits of satellite galaxies and stellar streams. Finally, there's the space between stars within the galaxy, the interstellar medium. This isn't empty vacuum, but rather a thin soup of gas and dust, mostly hydrogen with traces of heavier elements. The interstellar medium is the raw material from which new stars form, recycled from old stars that have died and returned their material to space. It's thicker and richer in the spiral arms, thinner in the spaces between them, but present throughout the galaxy, a reminder that space is never truly empty. All of these components, the bulge, the disk, the arms, the halo, the dark matter, work together to create a stable, long-lived structure. The Milky Way has existed for approximately 13 billion years, almost as old as the universe itself, and barring a major collision, it could persist for billions of years more. It's a remarkable piece of cosmic engineering, held together by gravity, powered by nuclear fusion, constantly recycling its material through cycles of stellar birth and death. And yet, for all its beauty and complexity, it's still just a medium-sized example of this type of structure. Which leads us to wonder, what determines a galaxy's size in the first place? Why are some galaxies enormous while others remain modest? The answer takes us back to the very beginning of cosmic time. Galaxies aren't created fully formed. They grow slowly and patiently over billions of years, accumulating mass through a complex process that astronomers are still working to fully understand. The story of any galaxy's size begins in the early universe, in the first few 100 million years after the Big Bang, when the cosmos was very different from the universe we see today. In those ancient times, the universe was smaller, denser, hotter, and remarkably smooth. But not perfectly smooth. Quantum fluctuations in the earliest moments of cosmic inflation created tiny density variations. Regions where matter was ever so slightly more concentrated than its surroundings. These variations were incredibly small, differences of just 1 part in 100,000, but they were enough. Gravity, patient and persistent, amplified these tiny differences over time. Where matter was slightly denser, it had slightly stronger gravity, which pulled in more matter, which increased the gravity further, which pulled in even more matter. This process, called gravitational collapse, created the first cosmic structures: dark matter halos, invisible gravitational wells where ordinary matter could collect and begin forming stars. The first galaxies were small, perhaps containing only a few million stars, nothing compared to the giants that would come later. But they were a beginning. These proto-galaxies grew through 2 primary mechanisms. The first was accretion, pulling in surrounding gas and dark matter. like a snowball rolling down a hill and gathering more snow. The second was mergers, collisions with other galaxies, violent events that combine two systems into one larger structure. Every large galaxy we see today, including the Milky Way, has likely absorbed dozens or hundreds of smaller galaxies throughout its history. The Milky Way is still absorbing galaxies today, slowly consuming its satellite galaxies, the Sagittarius Dwarf Elliptical Galaxy, the Canis Major Dwarf Galaxy, and others, each one adding its stars to our collection. But here's what's crucial to understanding galactic size. Not all regions of the early universe had the same density of matter. Some regions were richer in material, with larger initial density fluctuations, while others were relatively poor. Galaxies that formed in matter-rich regions had more fuel for growth. They could accrete more gas, form more stars, and grow larger through mergers. Galaxies that formed in less dense regions, like the Milky Way, had less material to work with. Location matters in galactic real estate just as it does in earthly real estate. The very largest galaxies, like IC 1101, formed at the centres of enormous galaxy clusters, where they could cannibalize hundreds of neighbouring galaxies and grow to monstrous sizes. These giant elliptical galaxies are sometimes called Quote 3 or BCGs, and they represent the ultimate result of galactic growth. Galaxies that have had billions of years and an abundance of neighbouring victims to consume. The Milky Way, by contrast, exists in what astronomers call the local group, a relatively modest collection of a few dozen galaxies dominated by just two large spirals, ourselves and Andromeda, with Andromeda being the larger of the two. We're not in a rich cluster environment. We're more like a suburb, comfortable and quiet, not a bustling downtown where galaxies crowd together. This has protected us from the merger mania that creates giant ellipticals, but it's also limited our growth potential. In a sense, the Milky Way's modest size was determined billions of years ago by where it happened to form, by the local density of matter in our region of the universe, by the accidents of cosmic geography that placed us in a quiet neighbourhood rather than a crowded city. We've grown steadily through slow accretion and the occasional absorption of small satellite galaxies, but we've never experienced the kind of massive mergers that create galactic giants. And perhaps there's something to appreciate in that, something worth contemplating as we move forward. The Milky Way's size isn't a failure or a deficiency. It's simply the natural result of its circumstances, its history, its place in the cosmos. And as we'll discover, being modest has its own advantages. Let's turn our attention now to the opposite end of the spectrum, to the true giants of the galactic world. If we want to understand what Quote 4 really means, we need to confront the sheer scale of galaxies like IC 1101, a galaxy so enormous that it challenges our ability to comprehend cosmic distances. IC 1101 resides at the heart of the Abell 2029 galaxy cluster, about 1 billion light-years from Earth. In the constellation Serpens, it's classified as a supergiant elliptical galaxy, a type of galaxy that has lost all trace of spiral structure and instead formed into a vast, roughly spherical or ellipsoidal collection of stars. Where spiral galaxies like the Milky Way have ongoing star formation in their spiral arms, elliptical galaxies are generally quiet, their star-forming days long past, populated mostly by older, redder stars that formed billions of years ago. The statistics of IC 1101 are almost absurd. The galaxy extends approximately 6 million light-years across, though that measurement depends somewhat on where you define the edge of the galaxy, always a slightly fuzzy boundary. To put that in perspective, IC 1101 is so large that the Milky Way, Andromeda, and the entire local group of galaxies, all 30-some galaxies in our cosmic neighbourhood, could fit comfortably within IC 1101's boundaries with room to spare. In fact, you could fit roughly 60 Milky Ways end-to-end across IC 1101's diameter. The stellar population is equally staggering. IC 1101 contains an estimated 100 trillion stars, though some calculations put the number even higher. That's approximately 400 times more stars than the Milky Way contains. The galaxy's central supermassive black hole weighs in at roughly 40 billion solar masses, 10,000 times more massive than Sagittarius A star. This black hole is so massive that its event horizon, the point of no return, is larger than the entire orbit of Pluto around our Sun. It's a cosmic monster that distorts space-time itself in its vicinity. But here's what's truly remarkable. IC1101 didn't start out this size. It grew to this enormous scale through countless mergers with other galaxies. Over billions of years, positioned at the centre of a rich galaxy cluster, IC1101's gravity pulled in neighbouring galaxies one by one, absorbing them, adding their stars to its collection, growing ever larger. Each merger was a catastrophic event on a galactic scale. Two or more galaxies colliding, their stars intermixing, their gas clouds compressing and igniting new star formation. Their supermassive black holes eventually spiralling inward and combining into one larger black hole. Imagine witnessing one of these mergers, not in human time but in cosmic time, sped up so that billions of years pass in moments. Two galaxies approach each other, their mutual gravity warping their shapes, pulling out long tidal streamers of stars. They interpenetrate, passing through each other like ghosts. Because the space between stars is so vast that direct collisions are incredibly rare. The galaxies swing around, their orbits decaying through the loss of energy, to gravitational waves and dynamic friction, and eventually they merge into a single, larger structure. Stars that once orbited in orderly spiral patterns now follow chaotic orbits in the merged elliptical galaxy. The gas clouds, compressed by the collision, ignite in a fierce burst of star formation that gradually dies down as the available gas is consumed or expelled. IC1101 has experienced this process not just once, but hundreds or possibly thousands of times. It's the accumulation of all those mergers, all that captured mass that created the giant we see today. In a very real sense, IC1101 is a graveyard, a final resting place for hundreds of galaxies that once had their own identities, their own structures, their own stories, and this, perhaps, is where we can start to find a different perspective on galactic size. IC1101 is undeniably impressive in its scale, but is it more beautiful than the Milky Way? Is it richer in complexity? Does its size make it more significant in any meaningful cosmic sense? Or is it simply larger, a product of location and circumstance, impressive in mass but not necessarily in meaning? Consider that the Milky Way is still actively forming stars, still creating new suns in its spiral arms, still evolving and changing. IC1101 is essentially finished, its star-forming days long past, its structure settled into a stable ellipsoid that will change very little over the coming billions of years, barring another major merger. Which is the more interesting galaxy? The answer isn't obvious, and we'll continue to explore this question as we move deeper into the night. IC1101 is remarkable, but it's not alone. The universe contains numerous galaxies that dwarf the Milky Way, each with its own fascinating characteristics. Let's explore a few of these giants, not to overwhelm ourselves with statistics, but to appreciate the sheer diversity of galactic forms that exist in the cosmos. NGC 6166, sometimes called the ultra-luminous infrared galaxy, stretches about 400,000 light-years across, 4 times the diameter of the Milky Way. It's not quite in IC1101's league, but it's still impressively large, and it has something that IC1101 lacks: violent ongoing star formation. NGC 6166 is the product of a relatively recent merger between two large spiral galaxies, and the collision has triggered an incredible burst of new star creation. The galaxy is forming new stars at a rate thousands of times faster than the Milky Way, turning its enormous reserves of gas into brilliant new suns at a prodigious rate. Then there's Hercules A, a giant elliptical galaxy located about 2 billion light-years away. The galaxy itself is enormous, containing trillions of stars, but what makes Hercules truly remarkable is what it's doing with all that mass. Its central supermassive black hole is actively feeding, pulling in enormous quantities of gas and matter, and this feeding process generates jets, narrow beams of high-energy particles that shoot out from the black hole's poles at nearly the speed of light. These jets extend over 1.5 million light-years into space on either side of the galaxy, creating vast lobes of radio emission that dwarf the galaxy itself. Or consider Messier 87, located about 53 million light-years away in the Virgo cluster. M87 gained fame in 2019 when the Event Horizon Telescope captured the first direct image of a black hole, showing the glowing ring of hot gas around M87's central supermassive black hole. The galaxy itself is a giant elliptical, containing several trillion stars, but it's the black hole that captures our imagination, a monster weighing 6.5 billion solar masses, with a visible jet shooting out 5,000 light-years into space. Each of these giant galaxies has its own story, its own unique characteristics, its own place in the cosmic ecosystem, but they share common traits that distinguish them from modest spirals like the Milky Way. They're massive, containing anywhere from several times to hundreds of times the mass of our galaxy. They're typically old, with most of their stars formed billions of years ago. They're often elliptical in shape, having lost their spiral structure through mergers, and they're usually found in rich environments, galaxy clusters where interactions and mergers are common. What's interesting is that these giants aren't necessarily the norm. When astronomers survey the universe and count galaxies, they find that most galaxies are actually quite small. Dwarf galaxies containing only millions or billions of stars rather than hundreds of billions are far more numerous than large galaxies like the Milky Way or giants like IC 1101. The distribution of galaxy sizes follows what statisticians call a power law, with many small galaxies, fewer medium galaxies, and relatively few giants. This means that while the Milky Way is small compared to the largest galaxies, it's actually quite large compared to most galaxies. We're in the middle of the distribution, perhaps even toward the larger end of typical galaxies. The giants like IC 1101 are outliers, exceptional cases rather than the standard. They're impressive, certainly, but they're also rare, products of specific circumstances and locations that most galaxies never experience. So when we say the Milky Way is embarrassingly small, we're not comparing it to the average galaxy. We're comparing it to the exceptions, the cosmic aristocrats, the galactic 1%ers. It's like feeling inadequate about your comfortable house, because somewhere there exist mansions and castles. Yes, those grand structures exist, and yes, they're larger than what you have. But does that diminish the value or the livability or the meaningfulness of your own home? We'll return to this question throughout the night, because it touches on something fundamental about how we measure worth and significance, not just in galaxies, but in life itself. For now, let's continue our exploration of what makes galaxies large or small, diving deeper into the mechanisms that govern galactic growth. To truly understand why some galaxies grow large while others remain modest, we need to talk about dark matter, the invisible substance that makes up most of the mass in the universe and plays a crucial role in galactic evolution. This might seem like a departure from our main story, but it's essential context, and I promise we'll keep it as gentle and accessible as possible. Dark matter is one of the most profound mysteries in modern physics. We can't see it. We can't touch it. We can't detect it directly with any instrument we've built, and yet we know it exists because of its gravitational effects on visible matter. Galaxies rotate too fast for the visible matter they contain. The outer edges should fly apart based on the mass we can see, but they don't, suggesting there's additional unseen mass providing extra gravity. Gravitational lensing, the bending of light by massive objects, shows more bending than visible matter alone can account for. The cosmic microwave background, the afterglow of the Big Bang, has patterns that only make sense if dark matter exists. The current scientific consensus is that dark matter makes up about 85% of all matter in the universe. Only 15% of matter is the ordinary stuff we're made of, atoms and molecules, protons and neutrons. The rest is something else, something that interacts gravitationally but not electromagnetically, meaning it doesn't emit, absorb, or reflect light. We don't know what dark matter is made of. Leading candidates include WIMPs, weakly interacting massive particles, and axions, hypothetical particles that would be extremely light and abundant. But despite decades of searching, we haven't detected dark matter particles directly. What we do know is that dark matter plays a crucial role in galaxy formation and growth. In the early universe, dark matter collapsed first, forming halos, gravitational wells where ordinary matter could then accumulate. These dark matter halos act like scaffolding, invisible frameworks that guide the formation of visible galaxies. The size and mass of a galaxy's dark matter halo significantly influences how large the visible galaxy can grow. In regions where dark matter halos are massive and concentrated, galaxies have deeper gravitational wells. They can hold on to more gas, resist having material stripped away by interactions with other galaxies, and capture more satellites. Over time, these advantages compound, allowing galaxies in rich dark matter halos to grow larger. Conversely, galaxies in less massive dark matter halos have shallower gravitational wells. They can't hold on to as much material, they're more vulnerable to having gas stripped away, and they grow more slowly. The Milky Way's dark matter halo is substantial, extending perhaps 600,000 light-years or more from the galactic centre, far beyond the visible edge of the galaxy at 50,000 light-years. This halo likely contains about 1 trillion solar masses of dark matter, compared to perhaps 60 billion solar masses of visible matter in stars and gas. The halo provides the gravitational stability that holds the galaxy together and governs the orbits of satellite galaxies. But compared to the dark matter halos of giant galaxies, the Milky Way's halo is modest. IC1101's dark matter halo likely contains tens of trillions of solar masses, providing a gravitational well so deep that it can capture and hold on to enormous amounts of matter. This massive halo is part of what enabled IC1101 to grow so large through mergers. It had the gravitational muscle to capture and retain all those other galaxies. There's something almost poetic about this. The visible galaxy, the thing we can photograph and observe, the beautiful spiral of stars and gas that we call the Milky Way, is really just the tip of the iceberg. Beneath and around it exists this vast invisible structure, this dark matter halo that shapes and constrains everything the visible galaxy can do. We're like a ship floating on an ocean, visible on the surface, but dependent on depths we cannot see and do not fully understand. And because we can't see dark matter directly, because we can only infer its presence through gravitational effects, there's an inherent uncertainty in all our measurements of galactic mass. When astronomers say the Milky Way contains 1 trillion to 1.5 trillion solar masses, that range reflects our uncertainty about exactly how much dark matter is present and how far the halo extends. The visible mass, the stars and gas we can observe, only accounts for about 5% of the galaxy's total mass. The other 95% is dark matter, invisible and mysterious. This means that when we compare galaxies by size, we're really comparing their dark matter halos as much as their visible components. A galaxy's size is determined not just by how many stars it contains, but by how massive and extended its dark matter halo is. And that halo, in turn, was determined by the density of dark matter in the region where the galaxy formed, by random fluctuations in the early universe, by cosmic accidents that occurred billions of years ago. The Milky Way is small, in part, because it formed in a region with a relatively modest dark matter halo. That's not a failure or a deficiency. It's just circumstance, cosmic geography, the luck of the draw in the early universe. And as we continue to explore this topic, we'll find that this perspective, this understanding of galaxies as products of circumstances, rather than achievements or failures, can be quite liberating. Let's bring our focus closer to home now. to the cosmic neighbourhood where the Milky Way resides. Understanding the local group, our small collection of galaxies, helps illuminate why the Milky Way has remained modest in size and what might lie in its future. The local group is a gravitationally bound collection of at least 80 galaxies, though many of these are tiny dwarf galaxies barely worthy of the name. The group spans about 10 million light-years across, roughly 1/16 the size of the Virgo supercluster, the largest structure we're part of. Within this volume, two large galaxies dominate, Andromeda and the Milky Way. Everything else is a supporting player, smaller galaxies orbiting one or the other of the big two or drifting in the space between them. Andromeda, as we mentioned earlier, is the larger of the two, containing perhaps 1 trillion stars compared to the Milky Way's 2 to 400 billion. It sits about 2.5 million light-years away, a distance that sounds vast but is actually quite close in cosmic terms. If you go outside on a dark, moonless night in the northern hemisphere, you can see Andromeda with your naked eye. A faint smudge of light in the constellation Andromeda. It's the most distant object visible to the unaided human eye, and the light you're seeing left that galaxy 2.5 million years ago, when our early human ancestors were just beginning to walk upright on the African savanna. The relationship between the Milky Way and Andromeda is complex. We're gravitationally bound, meaning that despite the expansion of the universe pulling most distant galaxies away from us, we and Andromeda are actually moving toward each other. Our mutual gravity is stronger than the cosmological expansion trying to separate us. Current calculations suggest we're approaching each other at about 250,000 miles per hour, a speed that sounds fast but is actually quite leisurely on cosmic scales. In roughly 4 billion years, give or take a billion years, the Milky Way and Andromeda will collide. This won't be a collision in the sense of cars crashing. Galaxies are mostly empty space, and the stars are spread so far apart that direct collisions between individual stars will be extremely rare. Instead, the galaxies will interpenetrate, passing through each other, their stars intermixing, their gas clouds colliding and triggering bursts of new star formation. After the first pass-through, the galaxies will swing back together, the merger process taking several billion years to complete. Eventually, the two spiral galaxies will combine into a single large elliptical galaxy, probably looking something like a smaller version of the giants we discussed earlier. Astronomers have even given this future galaxy a name, Milky, a portmanteau of Milky Way and Andromeda. Our Sun and solar system will likely survive this process, flung into some new orbit within the merged galaxy, probably farther from the centre than we are now. This future merger will make the Milky Way larger, combining our mass with Andromeda's to create something more substantial. But even Milky won't be a giant by cosmic standards. The combined galaxy will contain perhaps 1.2 to 1.5 trillion stars, impressive but nowhere near the 100 trillion of IC 1101. We'll move from being small to being medium-sized, a step up but not a revolutionary change. The rest of the local group consists of smaller galaxies, most of them satellites of either the Milky Way or Andromeda. The Milky Way has at least 59 known satellite galaxies, though the exact number keeps growing as we detect ever fainter dwarf galaxies in our vicinity. The largest of these is the Large Magellanic Cloud, visible from the southern hemisphere as a cloud-like patch in the sky, containing about 30 billion stars. There's also the Small Magellanic Cloud, and dozens of ultra-faint dwarf galaxies with names like Segway 1, Cansvenatici 1, and Boötes 1, some containing as few as 1,000 stars. These satellite galaxies are slowly being consumed by the Milky Way. Tidal forces from our gravity are stretching them, pulling them apart, creating long stellar streams that eventually merge with our galaxy's halo. The Sagittarius Dwarf Elliptical Galaxy is in the process of being torn apart right now, its stars gradually mixing with ours. In a sense, the Milky Way is still growing, still absorbing smaller galaxies, still accumulating mass, but at a much slower rate than the giants in rich clusters. What's notable about the local group is its relative isolation. We're not part of a rich galaxy cluster. The nearest large cluster, the Virgo cluster, is about 50 to 60 million light-years away, far enough that we're not strongly influenced by its gravity. This isolation has been both a blessing and a limitation. It's protected us from the merger mania that creates giant ellipticals, allowing the Milky Way and Andromeda to maintain their spiral structures for billions of years. But it's also limited our growth potential, because there simply isn't that much nearby material to absorb. In cosmic real estate terms, we're in a quiet suburb, while the giant galaxies live in dense urban centres. Both locations have their advantages. The suburbs are calmer, less chaotic, more stable. The urban centres are more dynamic, more eventful, but also more violent. Neither is inherently better or worse. They're just different environments with different characteristics. And perhaps that's a lesson worth absorbing as we continue. The Milky Way's size isn't a judgment on its value or its importance. It's simply a reflection of where it formed and what its circumstances have been over billions of years. We're small because we live in a quiet neighbourhood, not because we're inadequate or unsuccessful. There's a peaceful kind of acceptance in that realisation, a recognition that sometimes circumstances matter more than ambition, and that's perfectly all right. Let's pause here and ask ourselves a fundamental question. Why do we care about galactic size in the first place? What makes us think that bigger is somehow better? That a galaxy containing 100 trillion stars is more impressive or more valuable than one containing a few hundred billion? This question goes deeper than astronomy. It touches on how we assign value and significance to things, how we measure worth and importance. In many ways, the obsession with size is very human. We live in a world where bigger often does mean better, more impressive, more valuable. Bigger buildings, bigger companies, bigger budgets. These things often correlate with power and influence in human affairs. We're pattern-seeking creatures who evolved in environments where larger predators were more dangerous and larger food sources were more valuable. Of course, we're drawn to superlatives, to extremes, to the biggest and the brightest and the most powerful. But galaxies aren't companies or buildings or animals. They're natural structures governed by physics and shaped by billions of years of evolution. Their size doesn't reflect ambition or achievement. It reflects circumstances, where they formed, how much matter was available, whether they experienced major mergers. A small galaxy isn't a failed large galaxy any more than a stream is a failed ocean. They're different things, shaped by different processes, serving different roles in the cosmic ecosystem. Consider what actually matters about a galaxy from a scientific perspective. Complexity matters. Diversity matters. The Milky Way, with its active star formation, its spiral structure, its ongoing evolution, is arguably more scientifically interesting than a giant elliptical like IC 1101. Giant ellipticals are impressive in mass, but they're also relatively simple. They're old evolved systems with little ongoing activity. Most of their stars formed billions of years ago. They're settled, static, finished. The Milky Way, by contrast, is dynamic. We have ongoing star formation in our spiral arms, with new suns being born constantly. We have a complex structure with distinct components: the bulge, the disk, the spiral arms, the halo. We have satellite galaxies being actively absorbed, their stars creating streams and structures in our halo. We're not finished. We're still growing, still evolving, still changing. From a scientific perspective, that makes us interesting in ways that giant ellipticals aren't. There's also the question of habitability. Where is life more likely to arise? In a giant elliptical galaxy full of old, metal-poor stars, or in a spiral galaxy like the Milky Way with ongoing star formation and metal-rich environments? The answer isn't certain, but many astrobiologists favour spiral galaxies. The metallicity, the abundance of elements heavier than hydrogen and helium, tends to be higher in spirals, and these heavy elements are essential for forming rocky planets and supporting complex chemistry. Furthermore, the zones of ongoing star formation in spiral arms while violent in astronomical terms. Create environments rich in the building blocks needed for planetary systems. Young stars have protoplanetary disks where planets can form. Older stars in giant ellipticals may lack these disks, and their planetary systems, if they exist, formed billions of years ago under different conditions with different elemental abundances. So if we care about the potential for life, about the possibility that intelligence might arise and contemplate the universe as we do, then perhaps modest spiral galaxies like the Milky Way are more important than giant ellipticals despite being smaller. Size becomes secondary to other characteristics: complexity, diversity, habitability, the capacity to support interesting phenomena. There's another consideration too: perspective. From within a galaxy, does its total size even matter? We, living in the Milky Way, can only see a tiny fraction of our galaxy directly. The interstellar dust between stars blocks visible light, limiting our view. We can map the galaxy using radio and infrared observations that penetrate dust, but we can't actually see most of our own galaxy the way we can see external galaxies like Andromeda. An intelligent species living in IC 1101 would face a similar limitation. They could deduce their galaxy's size through careful observation and mapping, but they wouldn't experience that size directly. Their night sky would show local stars, just as ours does. The fact that their galaxy contained 100 trillion stars instead of a few hundred billion wouldn't affect their daily experience or their local environment. In fact, living in a giant elliptical might be somewhat boring. With little ongoing star formation, few spiral structures, and an older stellar population, the night sky in a giant elliptical would be dominated by yellower, older stars. There would be fewer bright blue young stars, fewer spectacular nebulae, less variety and drama in the local cosmic environment. The Milky Way's spiral structure, its star-forming regions, its diverse stellar populations, create a richer, more varied cosmic environment to study and appreciate. So we return to our question: why does size matter? And the answer we're arriving at, slowly and carefully, is that perhaps it doesn't, not in the ways we initially assume. The Milky Way is small compared to the largest galaxies in the universe, yes, but it's also complex, dynamic, interesting, and quite possibly more conducive to the emergence of life and intelligence than many larger galaxies. Its modest size isn't a deficiency. It's simply one characteristic among many, and not necessarily the most important one. As we move into the second half of our journey tonight, we'll explore this idea further, looking at what the Milky Way's size means for us specifically, for our planet, our solar system, our existence. We'll find, I think, that being in a small galaxy has its advantages, and that the cosmic address we occupy, while humble, is actually rather special in its own right. Let's travel back now to the beginning, to the first billion years after the Big Bang, when galaxies were just beginning to form. This epoch, so distant in time that light from those earliest galaxies is only just reaching us now, 13 billion years later, holds the key to understanding why galaxies like the Milky Way exist at all, and why they come in such different sizes. The universe at its beginning was remarkably simple. In the first few minutes after the Big Bang, nuclear fusion created the lightest elements: hydrogen, helium, and trace amounts of lithium and beryllium. That was it. No carbon, no oxygen, no iron. None of the heavy elements that make up planets and bodies and everything we touch. The early universe was just hydrogen and helium, cooling slowly as it expanded. For several 100,000 years, the universe was opaque, filled with a hot plasma of electrons and atomic nuclei that scattered light constant. Then, as temperatures dropped to about 3,000 degrees, electrons combined with atomic nuclei to form neutral atoms, and the universe became transparent. Light could finally travel freely through space. This moment, called recombination, created the cosmic microwave background, the afterglow of the Big Bang that we can still detect today, now cooled to just 3 degrees above absolute zero. But there were no stars yet. For roughly 200 million years after a combination, the universe existed in a state cosmologists call the cosmic dark ages. The universe was filled with neutral hydrogen gas, gently collapsing into the dark matter halos that would eventually host galaxies, but there were no sources of light. No stars, no galaxies, just darkness, punctuated by the faint glow of the cosmic microwave background, which would have appeared as a dim red glow filling the entire sky, dimming as the universe expanded and cooled. The Dark Ages ended when the first stars ignited. These were nothing like the Sun. They were massive, perhaps 100 to 300 times the mass of the Sun, made purely of hydrogen and helium with no heavy elements. They burned incredibly hot and bright, emitting intense ultraviolet radiation that began ionizing the hydrogen gas around them, turning it back into plasma. These first stars, called Population 3 stars, were also short-lived, burning through their fuel in just a few million years before exploding as supernovae. Those supernova explosions were crucial. They created the first heavy elements: carbon, oxygen, silicon, iron, scattering them into the surrounding gas. The next generation of stars could form from this enriched material, and with each cycle of stellar birth and death, the universe became more chemically complex. Heavy elements accumulated, dust grains formed, and the conditions for forming smaller, longer-lived stars like our Sun gradually emerged. The first galaxies were tiny by today's standards, perhaps containing only a few million stars, far smaller than even the smallest dwarf galaxies we see in the local universe today. But they were beginning. They had dark matter halos that provided gravitational scaffolding. They had gas that could form stars. They had supermassive black holes already growing at their centres, though how these black holes formed so early remains one of cosmology's mysteries. These proto-galaxies grew through the two mechanisms we mentioned earlier: accretion and mergers. They pulled in surrounding gas, forming new stars and growing larger. They collided with neighbouring proto-galaxies, merging into progressively larger structures. This process created a hierarchical pattern of galaxy formation, with small galaxies merging into medium galaxies merging into large galaxies, and so on. But here's the critical point. Not all proto-galaxies followed the same path. Those that formed in dense regions where dark matter and gas were abundant grew quickly. They experienced frequent mergers and had plenty of fuel for star formation. Those that formed in less dense regions grew more slowly. The Milky Way's progenitors were somewhere in the middle, not in the densest regions, but not in the most isolated either. Recent observations from the James Webb Space Telescope have revealed something surprising. There were relatively large, well-formed galaxies existing much earlier than our theories predicted. Galaxies that appear to have hundreds of millions or even billions of stars were already present just 400 to 500 million years after the Big Bang, during what should have been the cosmic dark ages or shortly thereafter. This challenges our understanding of how quickly galaxies could form, and suggests that galaxy growth in the early universe was faster and more efficient than we thought. What this means for our story is that galactic size was, to some extent, determined very early. Galaxies that got a head start in the first few 100 million years, that formed in regions with abundant dark matter and gas, had an advantage that compounded over billions of years. Galaxies that formed later or in less favourable conditions remained smaller. The Milky Way, formed sometime in the first billion years after the Big Bang, was moderately successful in this early competition for growth, successful enough to become one of the larger galaxies in the local universe, but not so successful that it became a giant. And there's something almost comforting in that. The realization that our galaxy's size was essentially determined 13 billion years ago by circumstances beyond any kind of control or intent. The Milky Way isn't small because it failed at anything. It's small because of where and when it formed, because of the local density of dark matter, because of random cosmic fluctuations that occurred in the first moments after the Big Bang. That's not failure. That's just history, the deep history of how structure emerged from the near-uniform soup of the early universe. As galaxies evolve over billions of years, they undergo a process that astronomers call chemical evolution. It's a gradual enrichment of the interstellar medium with heavy elements, created in stars and distributed through supernovae, and it tells us a great deal about a galaxy's history and size. Let's explore this concept carefully, because it connects to why the Milky Way's modest size might actually be an advantage. When we say metals in astronomy, we mean something different from everyday usage. In astronomy, a metal is any element heavier than hydrogen and helium. So carbon is a metal, oxygen is a metal, iron is a metal. This might seem strange, but it makes sense in context. Hydrogen and helium were created in the Big Bang, while all heavier elements were created later in stars. The first generation of stars, those population 3 stars we discussed, were made purely of hydrogen and helium. When they exploded as supernovae, they scattered newly created heavy elements into the surrounding gas. The second generation of stars formed from gas slightly enriched with these metals. When those stars died, they added even more metals. Each successive generation of stars forms from gas that's progressively more metal-rich, creating what astronomers call an Age-Metallicity Relationship. In the Milky Way, we can observe this relationship directly. The oldest stars in our galaxy, found in globular clusters and in the halo, have very low metallicity. Sometimes less than 1/100th the metallicity of the Sun. These ancient stars formed 10 to 12 billion years ago from gas that had experienced only a few cycles of stellar birth and death. They're almost pure hydrogen and helium, with just traces of heavier elements. Younger stars, particularly those in the galactic disk where the Sun resides, have much higher metallicity. The Sun itself is about 4.5 billion years old, middle-aged by stellar standards, and it has roughly solar metallicity, defined as 1.0 in the astronomical scale. Stars forming today in the Milky Way's spiral arms have even higher metallicity, benefiting from billions of years of chemical enrichment. This progression from metal-poor to metal-rich tells us about the Milky Way's star formation history. Unlike giant elliptical galaxies, which formed most of their stars in a brief burst billions of years ago and have been relatively quiet since, the Milky Way has maintained steady, ongoing star formation throughout its history. We've been slowly but continuously converting gas into stars, enriching the interstellar medium with metals, and creating progressively more metal-rich stellar generations. Why does metallicity matter? For several reasons. First, metallicity affects star formation itself. Gas clouds with higher metallicity can cool more efficiently, allowing them to collapse and form stars more easily. The presence of heavy elements, particularly carbon and oxygen, enables cooling through molecular emission, radiating away energy and allowing clouds to contract. This means that metal-rich galaxies can form stars somewhat more efficiently than metal-poor ones. Second, metallicity is crucial for planet formation. Rocky planets like Earth are made primarily of heavy elements: iron, silicon, oxygen, magnesium, and others. Gas giant planets have hydrogen and helium envelopes, but they likely formed around rocky cores. In the metal-poor environment of the early universe, rocky planets might have been rare or non-existent. As metallicity increased over cosmic time, the formation of planetary systems like our solar system became more probable. Third, metallicity affects habitability. The chemistry of life as we know it requires heavy elements: carbon for organic molecules, oxygen for oxidation and respiration, nitrogen for amino acids and DNA, phosphorus for energy storage, and others. A metal-poor environment would be very challenging for life to emerge. High metallicity provides the raw materials necessary for complex chemistry and biology. The Milky Way's steady, ongoing star formation, its gradual chemical enrichment, has created ideal conditions for the emergence of life. By the time the Sun formed 4.5 billion years ago, the local interstellar medium had reached solar metallicity, providing ample heavy elements for forming rocky planets and supporting complex chemistry. We're living in a galaxy at a point in its evolution when conditions are optimal for planetary systems and life. Giant elliptical galaxies, by contrast, formed most of their stars quickly, 10 to 12 billion years ago, during an intense starburst phase. They rapidly converted most of their gas into stars and then, having exhausted their fuel, became relatively quiet. Their stars are old, and while they've enriched the remaining gas with metals, there isn't much star formation happening now to create new planetary systems. If life requires planets forming around stars with sufficient metallicity, and if that requires billions of years of gradual chemical enrichment, then giant ellipticals might be less favourable environments for life than spiral galaxies like the Milky Way, despite being much larger. There's also the question of stellar density. In the central regions of giant elliptical galaxies, stars are packed extremely tightly, sometimes with less than a light year between neighbouring stars. This creates a harsher radiation environment, with more frequent close encounters between stars, more supernovae, more disruption to planetary systems. The Milky Way, being smaller and having a more spread out stellar distribution, provides a gentler, more stable environment where planetary systems can form and persist without constant disruption. So once again, we find that the Milky Way's modest size, rather than being a disadvantage, might actually be beneficial for the emergence and persistence of life. We're not in a violent, densely packed giant elliptical. We're in a medium-sized spiral with steady star formation and gradually enriching metallicity, precisely the kind of environment that seems most conducive to the complex chemistry and stable planetary systems that life requires. This doesn't mean giant ellipticals can't harbour life. We don't know enough to rule that out, but it does suggest that size isn't the determining factor for a galaxy's ability to host life. Other characteristics, star formation history, chemical evolution, stellar density, might matter much more, and in those characteristics the Milky Way excels, not despite its modest size, but perhaps in part because of it. Building on what we just explored, let's develop the idea that the Milky Way might be a quote 10, not too large, not too small, but just right for supporting life and intelligence. This concept, while speculative, offers a refreshing perspective on what galactic size really means. Let's start with what's too small. Dwarf galaxies, those tiny collections of a few million to a few billion stars, face several challenges. They have shallow gravitational wells, meaning they struggle to hold onto gas and heavy elements. When massive stars explode as supernovae in a dwarf galaxy, the explosion can blow gas completely out of the galaxy, a process called a supernova-driven wind. Once that gas is lost, it's difficult to recapture it, limiting future star formation. Dwarf galaxies also tend to have lower metallicity. With less ongoing star formation, and less mass to retain supernova ejecta, they don't undergo the chemical enrichment that larger galaxies experience. Many dwarf galaxies have metallicities well below solar, sometimes 1/10 or 100th of the Sun's metallicity. This makes forming rocky planets more difficult and challenges the emergence of complex chemistry. Furthermore, dwarf galaxies often experience tidal interactions with larger neighbours. The Milky Way's satellite galaxies, like the Magellanic Clouds, are being gravitationally disrupted, their stars and gas being pulled into stellar streams. Living in a dwarf galaxy might mean your galaxy is in the process of being torn apart by a larger neighbour, hardly a stable long-term environment. Now consider what's too large. Giant elliptical galaxies, as we've discussed, have their own challenges. They formed most of their stars early, meaning most of their stellar population is old, and there's little ongoing star formation to create new planetary systems. Their central regions are extremely dense, with close stellar encounters potentially disrupting planetary orbits. They often host very active supermassive black holes, with powerful jets and intense radiation that could be harmful to life. Giant ellipticals also tend to be located in dense galaxy clusters, violent environments where galaxy mergers and interactions are common. Intergalactic gas in clusters is often extremely hot, heated to millions of degrees by gravitational compression, making it difficult for galaxies to accrete new material. Living in a giant elliptical in a rich cluster would mean existing in one of the most energetic and violent environments in the universe, with constant disturbances from neighbouring galaxies. The Milky Way sits comfortably between these extremes. We're large enough to have retained our gas and undergone substantial chemical enrichment, building up the metallicity necessary for rocky planets and complex chemistry. We're small enough to maintain a relatively peaceful existence in the local group, avoiding the merger mania of rich clusters. We have ongoing star formation, creating new stars and new opportunities for planetary systems. We have a diverse stellar population, from ancient metal-poor stars to young metal-rich stars, providing a range of environments and timescales. Our location in the local group is also advantageous. We're not isolated like some field galaxies that drift alone through intergalactic space with no companions. We have Andromeda as a large neighbour, providing gravitational interaction that may have stimulated star formation at various points in our history. We have numerous satellite galaxies that we're slowly absorbing, adding their stars and heavy elements to our collection. But we're not in a crowded cluster where violent interactions are frequent. Even our position within the galaxy matters. The Sun sits in the Orion Arm, about 26,000 light-years from the galactic centre, in what's called the Galactic Habitable Zone. We're far enough from the centre to avoid the intense radiation and frequent supernovae of the inner galaxy, but we're not so far out in the halo that metallicity is too low for rocky planets. We orbit through the spiral arms periodically, but we spend most of our time in the relatively calm spaces between arms, avoiding the most violent star-forming regions. This concept of a galactic habitable zone suggests that not all locations within a galaxy are equally favourable for life. The inner regions might be too violent, too radiation intense. The outer regions might be too metal poor, too sparse. There's a quote 11 at intermediate radii where conditions are most favourable, and Earth happens to reside in that zone within a galaxy that's itself a sweet spot in the range of galactic sizes. Some astrobiologists have taken this idea further, suggesting that the Milky Way's characteristics might make it particularly favourable for the emergence of intelligent life. We have had billions of years of stable star formation, allowing multiple generations of stars and the gradual accumulation of planets. We've had enough time for metallicity to rise to levels that support rocky planets and complex chemistry. We've avoided major mergers for the last several billion years, providing stability during the time life was evolving on Earth. This doesn't mean the Milky Way is unique, or that only galaxies like ours can harbour life. The universe contains billions of galaxies, and many of them are similar to the Milky Way in size and structure. But it does suggest that our galaxy's characteristics, including its modest size, might be part of what makes Earth and life possible. We're not embarrassingly small. We're exactly the right size to provide a stable, enriched, diverse environment where life can emerge and evolve over billions of years. There's something deeply satisfying in this realization, the idea that we don't live in a cosmic backwater or a failed giant, but in a galaxy that's perhaps optimized for the very thing that makes the universe interesting, the emergence of minds that can contemplate their own existence and wonder about their place in the cosmos. Throughout this journey, we've mentioned galaxy mergers several times as one of the primary mechanisms by which galaxies grow larger. Let's explore this process in more detail now, understanding what happens when galaxies collide and why the Milky Way has avoided major mergers for most of its history. Galaxy mergers are among the most spectacular events in the universe. When two galaxies collide, several things happen simultaneously. First, despite the name collision, direct contact between stars is incredibly rare. Stars are so small compared to the distances between them that two galaxies can interpenetrate almost like ghosts passing through each other. If you were watching from a planet during a galaxy merger, you wouldn't see stars crashing into each other. You'd see the general pattern of stars in the sky slowly changing over millions of years as the two galaxies' gravitational fields interacted. But while stars rarely collide, gas clouds do. The interstellar medium in two merging galaxies does experience direct collisions, and when gas clouds moving at hundreds of kilometers per second slam into each other, they compress dramatically. This compression triggers intense star formation, a process called a starburst. Galaxies undergoing mergers can form stars at rates hundreds or thousands of times higher than the Milky Way's current rate, rapidly converting their gas reserves into new stars. These starbursts create spectacular fireworks, hot, blue, massive stars that illuminate the merger in ultraviolet light, followed by supernovae as those massive stars quickly die. The merger region becomes one of the most energetic environments in the universe, blazing with star formation and supernova explosions. But this phase is temporary. Once the gas is consumed or expelled, star formation drops dramatically, and the merged galaxy settles into a quieter state. The morphology of the merged galaxy depends on the sizes and orientations of the original galaxies. When two spiral galaxies of similar size collide head-on, the result is typically an elliptical galaxy. The ordered rotation of the spiral structures is destroyed, replaced by random stellar orbits in the elliptical. When a large galaxy merges with a much smaller one, a process called minor merging, the large galaxy can often retain its spiral structure, with the smaller galaxy simply adding stars to the larger one's population. This is fortunate for us, for life on Earth specifically. A major merger would trigger intense star formation in our galactic neighbourhood, creating many massive stars that would later explode as supernovae. The rate of supernovae in the galaxy could increase dramatically during a merger. Each supernova emits intense radiation, including gamma rays that could damage planetary atmospheres and harm life. A nearby supernova, within a few tens of light years, could potentially cause a mass extinction event on Earth. Furthermore, the gravitational disruption of a major merger could alter the Sun's orbit, possibly moving us closer to the galactic centre where the radiation environment is harsher, or farther out where metallicity is lower. The calm stability of our current orbit, safely tucked in the galactic habitable zone, could be lost. The Milky Way's lack of major mergers is a consequence of our location in the local group. We're not in a rich cluster where galaxies are crowded together and mergers are frequent. We have only one comparably sized neighbour, Andromeda, and that merger is still billions of years in the future. This isolation has allowed us to evolve in relative peace, maintaining our spiral structure, forming stars steadily, and providing a stable environment for planets and life. In 4 billion years, when the Milky Way and Andromeda finally do merge, Earth may no longer harbour life for entirely different reasons. The Sun will be nearing the end of its main sequence lifetime, growing brighter and eventually becoming a red giant that will render Earth uninhabitable. Whether life still exists in the Milky Way during the Milky-Meter merger is uncertain, but if it does, those living beings will witness a spectacular transformation of their cosmic home. Until then, we exist in a window of galactic stability, a period when the Milky Way is avoiding major disruptions and maintaining the kind of environment where life can thrive. Our modest size and quiet location have been essential to this stability, suggesting once again that being small has been an advantage, not a disadvantage for our existence. Let's turn our gaze forward now to the future of our galaxy. What does the Milky Way's modest size mean for its future evolution? How will it change over the next billions of years, and what can that teach us about galactic life cycles? The most dramatic event in the Milky Way's future is the merger with Andromeda, scheduled for roughly 4 billion years from now. We've mentioned this several times, but let's consider it more carefully. Current observations suggest that Andromeda is approaching us at about 250,000 miles per hour. That sounds fast, but at cosmic distances it translates to a very slow approach. Andromeda's apparent position in our sky is changing, but so slowly that you couldn't detect it even over a human lifetime. Computer simulations of the Milky Way-Andromeda merger, and astronomers have run many such simulations, suggest the process will take several billion years from first approach to final coalescence. The galaxies will have multiple close passes, each one stripping away stars and gas through tidal forces, before they finally settle into a single merged structure. During these close passes, our view of the night sky will be dramatically altered. Andromeda will grow larger in our sky, eventually filling a substantial portion of the heavens, a spiral of stars visible to the naked eye in stunning detail. The merger will trigger star formation, though whether Earth will still be habitable by that point is doubtful for other reasons. The Sun will be approaching the end of its main sequence lifetime, growing brighter and hotter. In about 1 billion years, the Sun's increasing luminosity will likely render Earth's oceans unlivable. In 5 billion years, the Sun will swell into a red giant, possibly engulfing Earth entirely. The Milky Way Andromeda merger will be well underway by then, but Earth's fate is more tied to the Sun's evolution than to galactic events. But let's imagine life persists somewhere in the merging galaxies, perhaps on planets orbiting longer-lived stars, or in artificial habitats constructed by advanced civilizations. What would they witness? They'd see the night sky becoming increasingly crowded as the two galaxies interpenetrate. They'd see spectacular bursts of star formation as gas clouds collide. They'd eventually find themselves living in Milkomeda, a large elliptical galaxy, no longer in the modest spiral of the Milky Way. The ultimate fate of the Milky Way, and Milkomeda, and indeed all galaxies, depends on the expansion of the universe. Current observations suggest the universe's expansion is accelerating, driven by dark energy, a mysterious force that pushes space itself apart. If this acceleration continues, galaxies will become increasingly isolated from one another as the space between them expands. Eventually, the local group will be alone, cut off from all other galaxy groups and clusters by the expansion of space. On timescales of Google years, 10 to the 100th years, an incomprehensibly vast duration, even black holes will evaporate through Hawking radiation, a quantum mechanical process that allows black holes to slowly lose mass. When the last black hole evaporates, the universe will enter its final era, the dark era, a cold, dark, nearly empty expanse where nothing interesting happens, where matter has decayed or dispersed, and only the faintest radiation persists. These distant futures are almost impossible to grasp emotionally. They extend so far beyond human or even planetary timescales that they seem more like abstract mathematics than actual futures. But they represent the ultimate fate of our galaxy, the end of the story that began with formation in the first billion years after the Big Bang. And yet, here, now, 13.8 billion years after the beginning, we exist in what might be called the galaxy's golden age. Star formation continues. The interstellar medium is rich with heavy elements. Planets orbit stable stars. Life has emerged and evolved to the point of being able to contemplate the galaxy it inhabits. The Milky Way is neither young nor old, but mature, complex, dynamic, interesting. Its modest size has contributed to this state, providing stability without stagnation, complexity without chaos. Perhaps being embarrassingly small in the present is exactly what allowed the Milky Way to become the kind of place where embarrassment, where consciousness, where wonder could exist at all. We've established that the Milky Way likely contains billions of potentially habitable planets, worlds where life could theoretically emerge and evolve. This raises one of the most profound questions in science. Where is everybody? This question, first articulated by physicist Enrico Fermi in 1950, has become known as the Fermi paradox, and it has interesting implications for our discussion of galactic size. The paradox can be stated simply. The Milky Way is billions of years old. If life is common, and if even a tiny fraction of life evolves intelligence and technology, and if even a tiny fraction of technological civilizations develop the ability and desire to explore and colonize other star systems, then where are they? Why don't we see evidence of advanced civilizations? Why aren't they here? Let's do some rough calculations to illustrate the paradox. Suppose there are 10 billion potentially habitable planets in the Milky Way, a conservative estimate based on exoplanet statistics. Suppose life emerges on just 1% of those planets. That's 100 million planets with life. Suppose intelligence evolves on just 1% of those. That's 1 million intelligent species. Suppose just 1% develop advanced technology and space travel. That's 10,000 technological civilizations. Now, the Milky Way is about 100,000 light-years across, even travelling at just 1% the speed of light, which is technologically challenging but not impossible according to known physics. A civilization could spread across the entire galaxy in 10 billion years. That sounds like a long time, but it's just 1,000th the age of the Milky Way. If advanced civilizations arise with any regularity, there's been plenty of time for them to colonize the galaxy, and yet we see no evidence of this. We've detected no alien signals despite decades of searching with SETI, the search for extraterrestrial intelligence. We see no evidence of large-scale engineering projects, no Dyson spheres capturing the output of stars, no obviously artificial structures. The galaxy appears silent, empty of intelligence beyond our own. This is the Fermi paradox. There are many proposed solutions to the paradox, and the fact that galactic size plays a role in this discussion is relevant to our story. One category of solutions suggests that intelligent life is extremely rare. Perhaps the emergence of life requires conditions so specific that it happens only once in a billion planets, or once in a galaxy. Perhaps intelligence is an extremely unlikely evolutionary outcome. Perhaps technological civilization is a brief, unstable state that most species pass through quickly, either destroying themselves or transforming into something we wouldn't recognize. If intelligent life is sufficiently rare, then the Milky Way's modest size actually increases the probability of being alone. A galaxy with 100 trillion stars like IC 1101 would have more opportunities for life to emerge, simply due to having more stars and more planets. The Milky Way, with its few 100 billion stars, might contain only one or a few technological civilizations at any given time, widely separated in space and time. Another category of solutions focuses on the difficulty of interstellar travel. Maybe travelling between stars is far harder than we imagine. Maybe it requires so much energy, so much time, so much risk that no civilization seriously attempts it on a galactic scale. Maybe civilizations turn inward, focusing on virtual realities or megastructures around their home stars rather than physical expansion. Or perhaps the Great Filter, a concept proposed by economist Robin Hanson, explains the silence. The Great Filter is some step in the evolution from non-living matter to spacefaring civilization that is extremely difficult to pass. If this filter is behind us, say the emergence of life itself or the evolution of intelligence, then we might be rare but have a promising future. If the filter is ahead of us, perhaps involving self-destruction through technology or some other barrier we haven't encountered yet, then civilizations might commonly reach our level but rarely go much further. The Milky Way's size is relevant to all these scenarios. In a smaller galaxy, distances between potential civilizations are smaller, making communication and contact more feasible. But there are also fewer stars, fewer planets, fewer opportunities for life to emerge. In a giant galaxy, there are vastly more opportunities, but distances are proportionally greater, making the galaxy harder to explore and more likely to contain isolated pockets of civilization that never contact each other. There's also the possibility that advanced civilizations are deliberately hiding or avoiding contact. Perhaps there's a galactic culture, a set of norms among spacefaring species that discourages interfering with developing civilizations. We might exist in a _14_ scenario, where we're being observed but not contacted. Or perhaps advanced civilizations have transcended physical form entirely, existing in ways we can't detect. What's interesting is that the Fermi paradox exists at all levels of cosmic structure. We can ask it about the solar system. Why don't we see alien artifacts in our solar system if civilizations colonize nearby stars? We can ask it about the Milky Way. Why don't we detect signals from anywhere in the galaxy? We could even ask it about the local group or Virgo supercluster. Why don't we see evidence of super civilizations that have colonized entire galaxies? The fact that we see no evidence at any of these scales suggests either that technological civilizations are extremely rare, or that they're deliberately quiet, or that there's some barrier we don't understand that prevents galaxy-wide expansion. And if civilizations are rare, then the Milky Way's modest size might mean we're truly alone in our galaxy, an isolated spark of consciousness in an otherwise lifeless collection of stars. This thought can be both lonely and profound. If we're alone, then the Milky Way, despite being embarrassingly small compared to cosmic giants, contains all the intelligence and consciousness in this region of the universe. Every thought, every piece of art, every scientific discovery, every moment of joy or wonder occurs here in our modest galaxy. That doesn't make us unimportant. It makes us the only sources of meaning in this entire structure, the only beings capable of asking whether the galaxy is large or small, whether that matters, what our place is in the cosmos. And if we're not alone, if there are others out there among the stars, then we're part of a galactic community we haven't yet discovered, living in a galaxy that's small enough to be comprehensible, explorable, potentially knowable. Either way, the Milky Way's size becomes not a source of embarrassment, but a feature of our cosmic home, appropriately scaled to our existence and our questions. As we contemplate the Milky Way's place in the universe, we need to consider a subtle but profound limitation on what we can ever observe or explore. The universe is not static. It's expanding, and more troublingly, that expansion is accelerating. This acceleration, driven by dark energy, means that most of the universe will eventually become permanently inaccessible to us, and the Milky Way's modest size takes on new significance in this context. Dark energy was discovered, almost by accident in 1998, by two independent teams of astronomers studying distant supernovae. They expected to find that the universe's expansion was gradually slowing down due to gravity, like a ball thrown upward eventually slowing and falling back. Instead, they found the opposite. The expansion is speeding up, as if some force is pushing space itself apart. This force, whatever it is, has been named dark energy, not because it's literally dark, but because we don't know what it is. It appears to be a property of space itself, a constant energy density that doesn't dilute as space expands. As the universe grows larger, there's more space, and therefore more dark energy, causing the expansion to accelerate ever faster. Dark energy makes up about 68% of the total energy in the universe, dominating both dark matter at 27% and ordinary matter at 5%. The implications of accelerating expansion are profound. Currently, we can observe galaxies billions of light years away. The farthest galaxies we've detected are about 13.4 billion light years away in terms of light travel time, meaning we're seeing them as they were 13.4 billion years ago when the universe was very young. But due to the expansion of space during the time the light travelled to us, these galaxies are now much farther away, about 32 billion light years in terms of current distance. As the universe continues to expand and accelerate, distant galaxies are being pushed away from us faster and faster. Eventually, they'll be receding faster than the speed of light. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself is expanding fast enough that the distance between us and distant galaxies increases faster than light can traverse it. When this happens, light from those galaxies will never reach us. They'll effectively disappear from our observable universe. Current models suggest that over the next few trillion years, all galaxies outside our local group will gradually fade from view, their light redshifted to longer and longer wavelengths until they're undetectable. The Virgo cluster, currently 50 to 60 million light-years away, will disappear. The Coma cluster, the Shapley supercluster, IC1101, All the distant giants we've discussed will fade beyond the cosmic horizon, their light unable to reach us across the ever-expanding gulf of space. Eventually, in about 100 trillion years, the only galaxies we'll be able to see will be those in our local group, the Milky Way, Andromeda, and a few dozen dwarf galaxies. By that time, the Milky Way and Andromeda will have merged into Milkomeda. From a planet in Milkomeda, looking up at the night sky, astronomers would see their own galaxy and a few small companions, but nothing beyond. The entire rest of the universe would be invisible. Cut off by the expansion of space, this means that civilizations arising in the far future will have a fundamentally different view of the universe than we do. They won't be able to see distant galaxies, won't be able to observe the cosmic microwave background, won't have the same evidence we have for the Big Bang or the age of the universe. They might conclude they live in a universe containing just their galaxy and empty space beyond. They would be wrong, but they'd have no way to know it. This future isolation gives the Milky Way's current modest size an interesting twist. Yes, we're small compared to the observable universe, but the observable universe is shrinking. As billions and trillions of years pass, fewer and fewer galaxies will be observable. Eventually only the local group will remain visible. At that point, being part of a quote 15 galaxy won't be a source of embarrassment because there will be nothing larger to compare it to. But there's a more immediate implication. We live in a special time in cosmic history, a time when the universe is old enough to contain complex structures like galaxies and planets, and life, but young enough that we can still observe most of the universe. In 1 trillion years, future civilizations won't have this privilege. We do. We can see IC1101 and marvel at its size. We can observe the cosmic web and understand large-scale structure. We can detect the cosmic microwave background and confirm the Big Bang. This makes our position in time, not just in space, privileged. We exist during the brief cosmic window, just a few trillion years long, when the universe is observable and comprehensible. The Milky Way's size, its structure, its place in the local group, all of this is part of a cosmic picture we're fortunate to be able to see. Later civilizations, if any arise, will have a much more limited view. So perhaps the question of whether the Milky Way is embarrassingly small should be reframed. We're not small in any absolute sense. We're appropriately sized for our era and our location. We're large enough to be interesting, small enough to be stable, and positioned in a way that allows us to observe and understand the universe around us. We exist at a time when that universe is still visible, still accessible to observation, still full of wonders to discover. Being part of the Milky Way, with all its modest characteristics, gives us a front-row seat to the cosmos during the brief period when such seats exist. That's not embarrassing. That's extraordinarily fortunate. We've travelled a long way together tonight, from the statistics of the Milky Way through comparisons with giants like IC1101, through the mechanisms of galaxy formation and evolution, through considerations of habitability and the Fermi paradox, through the far future when dark energy isolates us from the wider universe. Throughout this journey we've been exploring a question that seems simple, but touches on something profound. Does size matter? Let's settle into this question now, slowly and thoughtfully, because the answer reveals something not just about galaxies, but about how we find meaning and significance in a universe of overwhelming scale. The Milky Way is small compared to the largest galaxies. This is an objective fact. IC1101 is 60 times larger in diameter and contains 400 times more stars. Those numbers are real. There's no disputing them. But what do they mean? What significance should we attach to them? In everyday human affairs, size often correlates with importance. Larger cities have more people, more economic activity, more cultural influence. Larger companies have more employees, more revenue, more market power. Larger buildings are more impressive, more expensive, more noticeable. We're conditioned to think that bigger equals better, more important, more worthy of attention and respect. But this heuristic breaks down when we leave human-scale concerns and enter the realm of cosmic structures. Galaxies aren't competing with each other. They don't have goals or ambitions. They don't measure success or failure. They simply exist. Products of the initial conditions and physical laws that governed their formation billions of years ago. IC1101 is large because it formed at the centre of a rich galaxy cluster, where it could cannibalize hundreds of neighbours. The Milky Way is smaller because it formed in a quieter region where fewer mergers occurred. Neither galaxy chose its fate. Neither galaxy succeeded or failed at being large. They're simply different products of different circumstances. Both equally valid outcomes of galaxy formation processes. When we call the Milky Way embarrassingly small, we're projecting human values onto non-human structures. We're assuming that size equals worth, that larger is better, that being modest is somehow a failure. But these are human constructs. The universe doesn't share them. From a cosmic perspective, the Milky Way and IC1101 are both collections of stars, gas, dark matter and black holes, governed by gravity and evolving over billions of years. One is larger, one is more complex. Neither is better or worse. Moreover, as we've explored throughout the night, the Milky Way's modest size has been essential to creating the conditions we observe. Its steady star formation has allowed chemical enrichment over billions of years, creating metallicity levels conducive to rocky planets. Its avoidance of major mergers has maintained stable spiral structure, preserving environments where planetary systems can form and persist. Its location in a quiet region of the cosmic web has protected it from the violent interactions common in rich clusters. If the Milky Way had been larger, if it had formed in a denser region, and grown through numerous major mergers, it might have become a giant elliptical by now, with most star formation in its past in a harsher radiation environment. Would that be better? From the perspective of hosting life? Probably not. From the perspective of scientific interest, arguably not. From any perspective other than sheer size, it's not clear that being larger would be an improvement. This suggests a different framework for thinking about galactic size and significance. Instead of asking, is the Milky Way large or small, we might ask, is the Milky Way suitable for its purpose? And what is that purpose? Well, we're part of that purpose. We're inhabitants of this galaxy, products of its stellar chemistry, beneficiaries of its stability. From our perspective, the Milky Way's purpose is to provide an environment where life can emerge, evolve, and contemplate its own existence. Viewed this way, the Milky Way is not just suitable but perhaps optimal. It's large enough to contain hundreds of billions of stars, creating vast opportunities for planets and life. It's small enough to maintain stable structure over the timescales life requires. It's complex enough to be interesting, with spiral arms and ongoing star formation and diverse stellar populations. It's located in a region where it can evolve without constant disruption. The Milky Way is exactly what it needs to be for us to exist within it and wonder about it. Its size is not an embarrassment, but a feature, one of many characteristics that together create the cosmic home we inhabit. If it were significantly different, we might not be here to ask whether it's large or small. There's a philosophical concept called the anthropic principle that addresses this kind of thinking. In its simplest form, the anthropic principle states that the universe must be compatible with the existence of observers within it. We shouldn't be surprised that the universe has properties that allow life to exist, because if it didn't, we wouldn't be here to observe it. This seems almost tautological, but it has profound implications. Applied to the Milky Way, the anthropic principle suggests that we shouldn't be surprised the galaxy has characteristics conducive to life, because if it didn't, we wouldn't exist to observe it. The Milky Way's size, its chemical evolution, its structure, its history, all of these are part of the set of conditions that made Earth and humanity possible. We're not randomly sampling from all possible galaxies. We're necessarily observing a galaxy that allows observers to exist. This doesn't mean the Milky Way was designed for us, or that we're special in some cosmic sense. There are likely billions of galaxies throughout the universe with similar properties, many of them hosting life, some possibly hosting intelligence. But it does mean that the characteristics of our galaxy, including its modest size, are part of the explanation for why we're here to contemplate it. So where does this leave us? We began the night by calling the Milky Way embarrassingly small, confronting the fact that our cosmic home is modest compared to the giants that exist elsewhere in the universe. We've explored what that size means, how it came to be, why it matters or doesn't matter. And we've arrived at a kind of peace with scale. An acceptance that size is just one characteristic among many, and not necessarily the most important one. The Milky Way is neither large nor small in any absolute sense. It's appropriately sized for what it is and what it contains. It's home to hundreds of billions of stars, planets beyond counting, at least one instance of life and intelligence, and the entire scope of human experience, history, art, science, love, and wonder. That's not embarrassing. That's remarkable. That's more than enough. As we enter the final portion of our journey together tonight, let's shift from scientific analysis to something more personal and philosophical. We've spent hours discussing the Milky Way's size, its structure, its evolution, its place in the cosmos. Now let's ask a different kind of question. What makes the Milky Way our home? And how does its modest size contribute to that sense of belonging? Home is a concept laden with meaning that goes far beyond physical location. Home is where you're safe, where you're known, where you belong. Home is familiar even when it's vast, comfortable even when it's imperfect. Home is defined not by grandeur but by connection, by memory, by the sense that this place, whatever its characteristics, is where you're meant to be. For humanity, home has expanded over time. Initially, home was a specific cave or shelter, then a village, then a region, then a nation. With the development of spaceflight and the iconic photographs of Earth from space, the entire planet became home, that beautiful blue marble suspended in the void, the only world we've ever known. And now, as our understanding of the cosmos deepens, we're beginning to think of the Milky Way as home, the galaxy that contains not just Earth, but the entire span of human exploration and awareness. The Milky Way is vast beyond human comprehension, and yet it's comprehensible in a way that larger cosmic structures aren't. We can map it, chart its structure, understand its components, trace its history, predict its future. It's large enough to inspire awe, but small enough to be knowable. This balance between vastness and knowability is part of what makes it feel like home, rather than an overwhelming alien environment. Consider the alternative. If we lived in IC 1101, with its 100 trillion stars spread across 6 million light-years, the scale would be so enormous that the galaxy would feel less like a home and more like an infinite, unknowable expanse. You could spend thousands of lifetimes studying IC 1101 and never come close to comprehending its full extent. The Milky Way, by contrast, is large enough to be endlessly fascinating, but small enough that we can imagine, in principle, eventually understanding it fully. There's also something to be said for the Milky Way's structure. As a spiral galaxy, it has organization, pattern, beauty. The spiral arms sweeping out from the central bar create a sense of order, or a visual logic that's aesthetically pleasing and scientifically informative. When we look at images of the Milky Way, reconstructed from observations and models, we see not a chaotic jumble of stars, but an elegant structure, a cosmic architecture that feels purposeful even though it arose through purely physical processes. This structural elegance extends to our location within the galaxy. We're positioned in the Orion Arm, a minor spur off the major Perseus Arm, about 26,000 light-years from the galactic centre. This places us in what's sometimes called the galactic suburbs, far enough from the centre to avoid intense radiation and frequent supernovae, but close enough to be part of the disk where star formation continues. It's a comfortable, stable location, neither too dangerous nor too isolated. From this position, we have a particular view of the galaxy that's become intimately familiar through astronomy and science fiction. The Milky Way as a band of light across the night sky, visible from dark locations, has inspired humans for millennia. Ancient cultures created myths to explain this river of light, this path across the heavens. The Greeks called it the Milky Way, imagining it as spilled milk from the goddess Hera. Hindu cosmology describes it as a dolphin made of milk. Chinese astronomy calls it the Silver River. These myths and names reflect humanity's long relationship with the galaxy, our home galaxy, even before we understood what it was. We've always known the Milky Way was there, have always felt its presence, have always sensed that it was important, special, meaningful. Modern astronomy has given us a scientific understanding of what we're seeing, but it hasn't diminished the sense of wonder and belonging. If anything, knowing that we're looking at billions of distant suns, each potentially hosting its own planets and stories, deepens rather than diminishes the experience. The Milky Way's modest size contributes to this sense of home in subtle ways. Because the galaxy is relatively small, its contents are somewhat accessible. The nearest star beyond the Sun, Proxima Centauri, is just over 4 light-years away. That's still an enormous distance by human standards, requiring thousands of years to reach with current technology. But it's not impossible to imagine future technologies that might make such journeys feasible. The Milky Way feels like something humanity might eventually explore, at least partially, given enough time and technological development. If we lived in a giant galaxy, the nearest stars might still be reachable, but the full extent of the galaxy would be so vast that comprehensive exploration would be inconceivable even on civilization timescales. The Milky Way's modest size keeps the dream of galactic exploration alive, even if that dream is centuries or millennia away from realization. There's also a psychological dimension to scale and home. Humans need to feel that their home is special, unique, theirs in some meaningful sense. The Milky Way, being modest in cosmic terms, being one of countless similar galaxies throughout the universe, might seem to undermine this specialness. But paradoxically, it does the opposite. The Milky Way is special precisely because it's our home, because it's where we arose and where we live. Its size or comparison to other galaxies doesn't change that fundamental fact. Every home is, in some sense, unique, not because of objective characteristics, but because of subjective connection and history. Your childhood home might have been architecturally ordinary, no grander than millions of other houses, but it was special to you because of the memories created there, the life lived within its walls. The Milky Way is our childhood home on a cosmic scale. The place where humanity and Earth came into being, where all our history unfolded, where everything we love and remember exists. That makes it special, regardless of how it compares to other galaxies. In the end, what makes the Milky Way our home isn't its size or structure or position in the cosmic web, though all those characteristics matter. What makes it home is that we're here, that this is where our story is happening, that when we look up at the night sky and see that band of light, we're seeing ourselves, our origins, our context, our cosmic address. The Milky Way is home because home is where you are, where you belong, where your story unfolds. And for humanity, that place is here, in this modest. Let's lean further into the philosophy we've been developing, exploring the idea that modest things that aren't the largest or the grandest or the most extreme, often possess a beauty and value that exceeds more impressive structures. This is true not just in galaxies, but in life, in art, in nature. In all the domains where humans make judgments about worth and beauty. Consider the moon. Earth's moon is relatively large for a satellite, but it's far from the largest moon in the solar system. Jupiter's moon Ganymede and Saturn's moon Titan are both substantially bigger. Yet the moon is special to us in ways that no other satellite can match. It's our moon. It's been a constant presence in human life since before we were human, governing tides, inspiring myths, marking time. Its modest size relative to Earth, about 1/4 Earth's diameter, creates a relationship between planet and satellite that's unusual and meaningful. The Moon is large enough to be prominently visible from Earth, creating spectacular eclipses and tidal effects. But it's not so large that it dominates Earth gravitationally or creates a chaotic orbital environment. It's just right. And its beauty, the way it glows in the night sky, the way it waxes and wanes through its phases, has nothing to do with being the largest or most impressive moon in the solar system. Its beauty is inherent, arising from its characteristics and our relationship with it. Or consider trees. The tallest trees on Earth are coast redwoods, reaching heights over 380 feet. These giants are undeniably impressive. Monuments of organic architecture that inspire awe in anyone who walks among them. But smaller trees, a graceful willow beside a stream, a gnarled oak that stood for centuries, a cherry tree in bloom, possess their own beauty that's no less valid than the redwoods. Beauty isn't proportional to size. It emerges from form, context, relationship, meaning. In art and architecture, some of the most beloved works are not the largest, but the most perfectly proportioned, the most thoughtfully designed, the most human in scale. The Parthenon, for all its grandeur, isn't trying to be the biggest temple possible. It's trying to achieve perfect proportions, harmony of elements, a sense of balance and beauty that transcends mere size. The Taj Mahal's beauty doesn't come from being the largest mausoleum ever built. It comes from its exquisite symmetry, its delicate decorative work, its relationship to water and light. Japanese aesthetics formalize this appreciation for modest, imperfect, impermanent things in the concept of wabi-sabi. Wabi-sabi finds beauty in simplicity, in age, in imperfection. In things that are humble and natural rather than grand and polished. A hand-thrown ceramic bowl with an irregular glaze embodies wabi-sabi. A weathered wooden fence embodies wabi-sabi. These things aren't impressive in scale or perfection, but they possess a depth of beauty that resonates with thoughtful observation. The Milky Way, viewed through this lens, embodies a kind of cosmic wabi-sabi. It's not the largest or most impressive galaxy. It's not perfectly symmetrical or flawless in structure. It has a somewhat lopsided distribution of mass, with one spiral arm thicker than others. Its central bar is modest. Its spiral structure is beautiful but not exceptional. And yet all these characteristics make it interesting, make it real, make it a place rather than an abstract geometric form. There's authenticity in the Milky Way's modesty, a sense that it's a real galaxy with a real history rather than some idealized cosmic structure. It's evolved naturally over billions of years, shaped by collisions and accretion and the steady pull of gravity. It bears the scars and asymmetries of that history. It's not a pristine, perfect spiral, but a living, evolving system that's been changed by its experiences, by the mergers it's undergone, by the matter it's captured, by the stars it's formed and lost. This authenticity is part of what makes the Milky Way beautiful, what makes it home. Perfect symmetry can be cold, abstract, inhuman. Imperfection, irregularity, the marks of history and change. These make something relatable, knowable, warm. The Milky Way's modest size and imperfect structure make it feel accessible in ways that an enormous, perfectly symmetrical giant galaxy might not. There's also the matter of sustainability and stability. In ecology and human design, we've learned that bigger isn't always better, that there are often optimal sizes for systems beyond which further growth becomes problematic. A city that's too large becomes difficult to manage, loses livability, creates problems that smaller cities avoid. An organism that grows too large faces physical constraints, square-cube scaling laws that make certain sizes impractical. Galaxies too may have optimal sizes for certain purposes. We've discussed throughout the night how the Milky Way's size has contributed to stable spiral structure, steady star formation, and favourable conditions for life. Perhaps medium-sized spiral galaxies represent an optimal balance, large enough to retain gas and sustain star formation, small enough to avoid the merger violence that creates ellipticals. If so, then the Milky Way's modest size isn't a deficiency, but an indication of optimization for a particular set of outcomes. This suggests a principle that applies beyond astronomy, that value and beauty aren't necessarily correlated with size or scale. The largest things might inspire awe, but the most beautiful, most livable, most meaningful things are often those that achieve balance, that embody moderation, that are just right for their purpose rather than extreme in any direction. The Milky Way is not embarrassingly small. It's appropriately modest, balanced between extremes, optimized for the role it plays in hosting stars and planets and life and consciousness. Its beauty doesn't come from being the largest, but from being what it is, a real galaxy with real history, a place with structure and story, a home that's large enough to inspire wonder, but small enough to feel like it could be known, explored, understood. As we spend these final chapters together drifting towards sleep, let this perspective settle over you, that modest things are not lesser things, that balance is often better than extremes, that being just right matters more than being the biggest, or the grandest, or the most impressive. The Milky Way, in all its modest glory, exemplifies this truth. And so do you, and so does Earth, and so does everything that matters in the universe. Size is just a number. Meaning is what we make of it. We're moving toward the end now, toward resolution and rest, and it feels appropriate to address directly the emotion implied in our title, embarrassment. Why would we feel embarrassed about the Milky Way's size? What does that embarrassment reveal about us, and how can we move beyond it toward acceptance and appreciation? Embarrassment is a social emotion, one that arises when we feel we've fallen short of some standard or expectation, particularly in a way that others might judge. We feel embarrassed when we make mistakes in public, when we're revealed to be less competent or knowledgeable than we appeared, when we're caught in a situation that exposes our vulnerabilities or inadequacies. Embarrassment assumes an audience, real or imagined, whose judgment we care about. So when we call the Milky Way embarrassingly small, what are we actually expressing? We're imagining some cosmic audience, perhaps inhabitants of IC 1101 looking down on our modest galaxy with disdain. We're projecting competitive social dynamics onto galaxies that don't compete, don't judge, don't care about size hierarchies. We're assuming that being small is a failure worthy of shame, that we should feel bad about our galaxy's modest dimensions. But this is entirely a human construction. Galaxies don't experience embarrassment. IC 1101 doesn't feel proud of its size. The Milky Way doesn't feel inadequate. These emotional responses exist only in our minds, products of our tendency to anthropomorphize, to project human values and emotions onto non-human phenomena. The universe doesn't judge, only we judge. And we can choose what judgments to make, what standards to apply, what matters and what doesn't. Let's consider an alternative framework, one rooted in acceptance rather than judgment, in appreciation rather than comparison. Instead of asking, is the Milky Way large or small, and implying a value judgment with the answer, we can simply observe, the Milky Way is this size, with these characteristics, in this location. Those are facts, neutral descriptions of reality. The judgment, the embarrassment, the sense that this is somehow inadequate, that's something we're adding, and we can choose not to add it. Acceptance doesn't mean resignation or settling for less. It means acknowledging reality as it is, without requiring it to be different to be acceptable. The Milky Way is the size it is because of its formation history, its dark matter halo, its location in the cosmic web. Those factors were determined billions of years ago by random fluctuations in the early universe. There's no blame, no failure, no inadequacy. There's just circumstance and physics, cause and effect, the unfolding of natural processes over cosmic time. When we accept the Milky Way's size as a fact rather than a judgment, we free ourselves to appreciate what the galaxy actually is rather than lamenting what it isn't. We can appreciate its spiral structure, its ongoing star formation, its chemical richness, its stability, its suitability for hosting life. We can appreciate that it's our home, the context for everything we know and love. We can appreciate that it's large enough to contain wonders we'll never exhaust, even as it's small enough to feel comprehensible. This kind of acceptance is liberating. It releases us from the burden of cosmic competition, from the need to rank our galaxy against others and feel pride or shame based on that ranking. It allows us to simply be here, in this galaxy, without needing it to be the largest or the best or the most impressive. It's enough that it's real, that it exists, that we're part of it. There's a parallel here to how we might think about our own lives and accomplishments. We live in a culture that often emphasizes achievement, success, being the best or the biggest or the most accomplished. We're encouraged to compete, to compare ourselves to others, to feel pride when we come out ahead and shame when we don't. But this framework, while sometimes motivating, can also be exhausting and ultimately unsatisfying. An alternative is to focus on being rather than achieving, on living well rather than surpassing others, on finding meaning in our actual experiences rather than in how they rank against alternatives. You don't need to be the most successful person in your field to live a meaningful life. You don't need to accomplish more than your peers to be worthy of respect and love. You need to be present, to engage with the world authentically, to create meaning through your relationships and actions and choices. The Milky Way, in its modest way, exemplifies this alternative framework. It's not trying to be IC1101. It's not competing to be the largest galaxy. It's simply existing, evolving, hosting stars and planets and life, doing what galaxies do without concern for rankings or comparisons. It doesn't need to be embarrassingly small or impressively large. It just needs to be itself. When we accept our place in the Milky Way, when we accept the galaxy's characteristics without requiring them to be different, we align ourselves with this cosmic equanimity, this fundamental okayness of things as they are. The Milky Way is this size. Earth orbits this star in this location. We're these particular beings in this particular place and time. None of that needs to be different to be acceptable, valuable, meaningful, beautiful. This acceptance extends to uncertainty as well. Throughout our conversation tonight, I've mentioned many numbers, many statistics about the Milky Way's size and mass and characteristics. But the truth is, many of these numbers are uncertain. We don't know exactly how many stars the Milky Way contains. The estimates range from 200 billion to 400 billion. We don't know exactly how much dark matter surrounds us. We don't know precisely when the merger with Andromeda will occur, or exactly what Milkomeda will look like. This uncertainty might seem frustrating, like a lack of knowledge we should remedy. But it can also be accepted as a fundamental feature of how we understand the universe. We're finite beings trying to comprehend structures of cosmic scale, and some uncertainty is inevitable. We do our best, we make measurements, we build models, we refine our understanding, but we accept that perfect knowledge is unattainable, and that's okay. That's part of being human, part of being conscious observers in a vast universe that exceeds our capacity to fully know it. So we arrive at acceptance, at peace with what is. The Milky Way is modest in size compared to the largest galaxies, and that's okay. It's our home, it's beautiful, it's sufficient for every purpose that matters to us. We don't need it to be larger to be proud of it, to appreciate it, to feel privileged to be part of it. Its size is what it is, and what it is exactly right for us, for now, for this moment in cosmic time when we're here to contemplate it. As we near the end of our journey together, I want to return to something we touched on earlier, the extraordinary privilege we have here and now to observe and understand the Milky Way and its place in the universe. This privilege is not just scientific or intellectual, it's existential, philosophical. A rare and precious opportunity that won't last forever and may not be shared by conscious beings at all times and places. Consider what's required for observation and understanding to be possible. First, you need observers, conscious, intelligent beings capable of asking questions about the universe and processing answers. The emergence of consciousness and intelligence is itself remarkable, possibly rare, certainly not guaranteed by physics alone. On Earth, it took billions of years of evolution to produce beings capable of contemplating the cosmos. Whether this is common elsewhere in the universe remains an open question, but it's clearly not trivial. Second, you need technology sufficient to observe beyond your immediate environment. For most of human history, our understanding of the cosmos was limited to what we could see with naked eyes. The invention of the telescope in the early 17th century was revolutionary, allowing us to see farther and more clearly. The development of spectroscopy, the ability to analyze the light from distant objects and determine their composition and motion, was equally revolutionary. Modern astronomy depends on technologies ranging from radio telescopes to space telescopes to gravitational wave detectors, each extending our reach and understanding. Third, you need to exist at a time when the universe is observable. We discussed earlier how dark energy will eventually make most of the universe unobservable, hidden beyond the cosmic horizon. But there's a more fundamental temporal constraint. The universe needs to be old enough to have formed complex structures, but young enough that those structures are still visible. Too early, and galaxies haven't formed yet. Too late, and they've faded from view. We exist in a window, perhaps a few trillion years long, when the universe is both interesting and observable. Fourth, you need favourable circumstances. A planet that's habitable, stable, located in a quiet region of its galaxy. A star that's long-lived and stable. A galaxy that hasn't been disrupted by recent mergers. Clear skies, dark locations away from light pollution, the ability to build observatories and dedicate resources to pure research without immediate practical application. All of these are contingent, could easily have been otherwise, and yet they're necessary for the kind of comprehensive understanding we've developed. When you put all these requirements together, the privilege becomes clear. We, here, now, on Earth in the 21st century in the Milky Way galaxy, are in an extraordinary position to observe and understand the cosmos. We have the intellectual capacity, the technology, the temporal positioning, and the favourable circumstances to map our galaxy, observe distant galaxies, understand cosmic history, predict cosmic futures. This is not something to take for granted. Future civilizations, if any arise in Milkomeda after the Milky Way-Andromeda merger, will have a fundamentally different perspective. They'll see a single large elliptical galaxy, a few satellite dwarfs, and empty darkness beyond. They might deduce that other galaxies once existed, now disappeared beyond the horizon, but they won't be able to observe them. They'll have access to far less cosmic information than we do, making certain questions harder or impossible to answer. Past observers, had any existed in the early universe, would have seen a cosmos in its infancy, with only primitive galaxies and no long evolutionary history to study. The complex structures we observe, the beautiful spirals and enormous ellipticals, the galaxy clusters and cosmic web didn't exist yet. The universe was interesting, but in different ways, and the particular beauty and complexity we can observe now wasn't yet present. This suggests that our position in cosmic history is uniquely privileged for observational astronomy. We exist at a time when the universe is mature enough to be maximally interesting, but young enough to be maximally observable. This may be a rare conjunction, a brief window in cosmic time when conditions align for comprehensive understanding, and we're living in that window. There's something deeply moving about this realization. It suggests that the Milky Way's modest size, far from being embarrassing, is part of a constellation of circumstances that make our existence and our understanding possible. We're in a galaxy that's stable enough to allow life to evolve over billions of years. We're We're in a region of the galaxy that's safe enough for planetary systems to persist. We're at a time in cosmic history when observation and understanding are maximally possible. And we're part of a species that has developed the curiosity and capability to observe and understand. This privilege carries with it a kind of responsibility, or perhaps more accurately, an opportunity. We have the chance to observe, to learn, to understand, to appreciate. We have access to cosmic knowledge that past beings couldn't have accessed, and future beings may not be able to access. What we do with that knowledge, how we respond to it, what meaning we find in it, that's up to us. Some will respond with wonder, with awe, at the vastness and complexity and beauty of the universe. Some will respond with curiosity, with a drive to learn more, to push the boundaries of understanding further. Some will respond philosophically, contemplating the implications of our place in the cosmos for questions of meaning and value and purpose. All these responses are valid. All honour the privilege we've been given. The Milky Way, in being the galaxy we observe from, in being our home and our context, is central to this privilege. Its modest size makes it comprehensible. Its structure makes it beautiful. Its stability makes it hospitable. Its position in cosmic history makes it observable. We're not just passive inhabitants of this galaxy. We're active observers, students of its nature, beneficiaries of its characteristics. That relationship, that engagement, transforms the Milky Way from an arbitrary cosmic structure into something meaningful, something that matters not just objectively but subjectively, not just scientifically but personally. As we prepare to conclude our time together, let this sense of privilege settle over you. You exist. You're conscious. You can observe the universe and understand something of its nature. You live at a time and place where comprehensive cosmic knowledge is possible. You're part of a galaxy that, while modest, is exactly suited to allow all this to happen. That's not embarrassing. That's miraculous. That's cause for gratitude, for wonder, for a profound sense of fortune at being here, now, in this moment, part of this cosmic unfolding. We've reached the final chapter of our journey, and it's time to bring everything together to find the thread that connects all we've explored tonight. We started with a question about size, about the Milky Way being embarrassingly small compared to cosmic giants. We've wandered through galaxy formation, chemical evolution, the search for life, the Fermi paradox, dark energy, and the nature of home. Now let's come full circle and discover what we've really been exploring all along. The Milky Way is small, that's a fact. But what we've learned tonight is that this fact, taken in isolation, means almost nothing. Size without context is just a number. The meaning emerges from how we think about that number, what we compare it to, what conclusions we draw, what emotions we attach to it. And we have a choice in all of that. We can choose to see the Milky Way as embarrassingly small, to feel shame or inadequacy at our galaxy's modest dimensions compared to IC1101 or other giants. We can imagine a cosmic hierarchy with large galaxies at the top, prestigious and important, and small galaxies at the bottom, diminished and unworthy of attention. We can project our human obsession with size and status onto inanimate structures of stars and dark matter that don't care about such things, or we can choose differently. We can see the Milky Way as appropriately sized for its role and circumstances, as a balanced, stable, complex structure that's provided a home for life and consciousness. We can appreciate that size is just one characteristic among many, and not necessarily the most important. We can recognise that our galaxy's modest dimensions have been essential to creating the conditions we enjoy, that being in a small galaxy has advantages that offset any disadvantages. More fundamentally, we can recognise that the very impulse to rank galaxies by size and assign value based on that ranking is a human imposition, a projection of our values onto a universe that doesn't share them. The universe doesn't rank galaxies, it simply contains them, allows them to form and evolve according to physical law, treats them all equally in the sense that gravity and dark matter, and physical processes apply everywhere without regard for size or status. What we've really been exploring tonight, beneath the discussions of galactic structure and star formation and dark energy, is how we find meaning in a universe of vast scale. How do we, as small beings on a small planet in a modest galaxy in an enormous universe, maintain a sense of significance, of purpose, of being part of something meaningful? How do we avoid being overwhelmed by cosmic scale, by the sheer vastness that makes our concerns seem trivial and our existence seem accidental? The answer we've been developing is that meaning doesn't come from size or scale. It comes from complexity, from relationship, from the intricate web of connections that make something more than just a collection of parts. The Milky Way is meaningful not because it's large or impressive, but because it's our galaxy, because we're part of it, because our existence and consciousness arose within its bounds and depends on its characteristics. Every star in the Milky Way, every planet, every gas cloud, every particle of dark matter is part of the structure that supports our existence. We're not separate from the galaxy, observing it from outside. We're inside it, made of it, constituted by atoms that were forged in its stars and scattered through its interstellar medium. The calcium in our bones, the iron in our blood, the carbon in our cells, all came from stars that lived and died in this galaxy billions of years ago. We are quite literally the Milky Way's way of knowing itself. Through us, through our observations and our understanding, the galaxy becomes aware of its own existence, its structure, its history, its place in the cosmos. That's not a diminishment of human significance. It's an elevation of both human and galactic significance. We matter because we're the means by which matter becomes conscious and contemplative. The galaxy matters because it's the context that made us possible. This perspective transforms the question of galactic size from a matter of pride or shame into something more subtle and profound. The Milky Way's size is part of what makes it suitable for this role, for hosting life and consciousness. Too large, and it might be too violent, too disrupted by mergers, too harsh in its central regions. Too small, and it might lack the chemical richness, the stellar diversity, the long history of star formation that seems necessary for complex life. The Milky Way is, in an important sense, just right. Not because it was designed to be, not because there's any cosmic purpose or plan, but because we're necessarily observing a galaxy that allowed us to exist. We couldn't be having this conversation in a galaxy that was unsuitable for life. The fact that we're here, wondering about the galaxy's size, is itself evidence that the galaxy's characteristics, including its size, are compatible with the emergence of observers. There's a kind of circular logic here, a self-referential loop that's characteristic of anthropic reasoning. We observe what we can observe, we exist where we can exist, we wonder about what allows us to wonder. It might seem tautological, but it's actually profound. It reminds us that we're not separate from the universe we study, that our observations are always observations from within, that our perspective is necessarily limited and shaped by our position. And in that recognition, we find a kind of peace. We don't need the Milky Way to be the largest galaxy to be significant. We don't need to rank first in some cosmic competition. We need only to be here, to exist, to observe, to understand, to find meaning in our particular circumstances. The Milky Way, in all its modest glory, provides exactly that opportunity. So we come home to where we've always been, to the Milky Way, our galaxy, our cosmic address. We've journeyed through discussions of giants and dwarfs, of formation and evolution, of habitability and future, but ultimately we've returned to a simple truth. We're here. This is home. And home is not diminished by being smaller than other places. Home is special because it's where we are, where we belong, where our story unfolds. The embarrassment we started with was misplaced, a projection of human insecurities onto cosmic structures that exist beyond such concerns. The Milky Way has no reason to be embarrassed. Neither do we. We're part of something vast and beautiful and ancient, a galaxy that's been evolving for 13 billion years and will continue for billions more. Our moment within that span is brief, but it's real, it's meaningful, it matters to us, and that's enough. As we prepare for the closing, as we move toward rest and sleep, let yourself settle into this acceptance. The Milky Way is home. It's exactly the size it needs to be. You're exactly where you need to be. Everything is as it should be, not perfectly, not ideally, but really authentically sufficiently. And in that sufficiency, that okayness of things as they are, there's a deep and abiding peace. Let that peace carry you now as we bring our journey to its close. And so we've travelled together through the cosmos, starting with a question about size and ending with an understanding of home. Thank you for staying with me through this entire 2.5-hour journey. That's a gift of time and attention, a commitment to contemplating our place in the universe, and I'm grateful you chose to spend this time here, drifting through these thoughts with me. We've moved from the statistics of the Milky Way. Its 200 to 400 billion stars and 100,000 light-year span, through comparisons with giants like IC 1101, through the mechanisms of galaxy formation and the gradual chemical enrichment that made life possible, through considerations of habitability and the Fermi paradox, through the far future when dark energy isolates us, through philosophical reflections on scale and meaning and home. From the cold numbers of astronomical measurement to the warm recognition that we're part of something vast and beautiful. The answer, as honestly as I can give it, to the question of whether the Milky Way should be embarrassed about its size is no. Emphatically, definitively, no. The Milky Way is exactly what it needs to be, shaped by billions of years of evolution, positioned in a quiet region of the cosmic web, hosting hundreds of billions of stars, including the one that warms Earth. Its modest size, far from being a deficiency, has been essential to creating the stable, complex, habitable environment where life could emerge and evolve to the point of wondering about galaxies and their sizes. We're not in a cosmic backwater. We're in a cosmic sweet spot, a galaxy that balances size with stability, complexity with comprehensibility, ancient history with ongoing evolution. The Milky Way is our home, and home is always special, always meaningful, regardless of how it compares to other places. We belong here. We arose here. Everything we know and love exists here, in this galaxy, on this planet, in this particular moment of cosmic time. If you've enjoyed this slow drift through space and time, a like and subscribe would be wonderful, truly helpful in reaching others who seek these calm explorations as their day ends. And to those who return night after night, to those familiar voices in the comments, thank you. You've become a community, fellow travellers through the cosmos, and there's comfort in knowing we're all here together, looking up at the same stars, wondering about the same mysteries. Wherever you are in the world right now, whatever time it is, whatever circumstances you're in, I hope you're comfortable. I hope your breathing has slowed and deepened over the course of our time together. I hope your thoughts, which might have been busy and tangled when we started, have settled into something calmer, more peaceful. I hope your body feels heavy and warm, ready for rest, ready to release the day and drift into sleep. Look up at the Milky Way if you can. If you're somewhere dark enough to see it, that band of light across the sky, that river of stars. Or imagine it, if you're indoors or in a city where light pollution hides the night sky. Picture those hundreds of billions of stars, those vast clouds of gas and dust, those spiral arms slowly turning through space. Picture the supermassive black hole at the centre. Sagittarius, a star, anchoring everything. Picture Earth, our pale blue dot, tucked safely in the Orion Arm, 26,000 light-years from the centre, orbiting a modest yellow star, hosting the only life we know for certain exists. All that vastness, all that complexity, all those billions of years of evolution, and it led to this moment. To you, lying here, listening to these words, contemplating your place in the cosmos. That's not insignificant. That's remarkable. That's the universe becoming aware of itself, matter contemplating matter, consciousness emerging from unconscious physical processes and turning its attention outward and inward simultaneously. The Milky Way is not embarrassingly small. It's magnificently sufficient. It's exactly what it needs to be to provide a home for stars and planets, and life and consciousness. Its modest dimensions are part of what makes it suitable for this role, part of what allows the stability and complexity we depend on. We're not living in a failed giant. We're living in a successful, thriving, beautiful spiral galaxy that's been our home for all of human history and will remain our home for as long as humanity exists. There's peace in that recognition, in accepting our galaxy as it is, in appreciating its characteristics without needing them to be different. The Milky Way is home. You are home. Right here, right now, in this moment, everything is as it should be. Not perfect, but real. Not ideal, but sufficient. And in that sufficiency lies a profound okayness, a fundamental peace with what is. So sleep well. Dream of stars and galaxies, of spiral arms and dark matter, of planets orbiting distant suns. Dream of the Milky Way, our modest, beautiful, endlessly fascinating home. Dream of Earth, that pale blue dot, and the life it hosts, including you, precious and significant and part of this vast cosmic unfolding. Good night. May you rest deeply. May you wake refreshed. May you carry with you, into tomorrow, the understanding that you're part of something vast and ancient and beautiful, and that's more than enough. More than enough. Good night.